Hi, my name is Sandra Pauletto, and together with Stephen Barras, I will take you through this short introduction titled From Sound Design to Sonification. We will cover some terminology, briefly mention how sound design and sonification developed historically. We will cover the main auditory display and sonification methods, and finally, we will discuss what links sonification and design research, all with some examples along the way. There are no generally accepted definitions of sound design. The one we will use here is a definition by Patrick Suzini from Earcons, which states that sound design means to make an intention audible. A designed sound is new and constructed, and it represents something other than the sound itself. This can be an object, a concept, or a system. And there are two intentions that need to be audible: form and function. To give an example, let's imagine the sound of a knock on a door. The sound tells us both about the function, someone wants to enter the room, and the form. The door is made of wood as opposed to glass. This information needs to be clearly heard and correctly interpreted for the design to be considered successful. Sound design begins in Greek and Roman times, with mechanical sound effects being created for theatrical representations. This tradition continued up until the beginning of the 20th century, when purposely made sound effect machines were used in theatre and silent cinema. In 1927, the film The Jazz Singer comes out. It marks the beginning of films being accompanied by synchronized sound. Around the same time, Jack Foley developed a technique of recording sound effects performed in synchronization to the picture that is still in use today. Foley artists are sound professionals who record in post-production everything from characters' footsteps to clothes movements, from object interactions to water splashes. The first credited film sound designer is Walter Murch, double Oscar winner for sound mixing and picture editing, famous for many films including The Conversation, Apocalypse Now, The English Patients, and more. For Murch, the role of the sound designer is that of the person who supervises the entire soundtrack, today often called the supervising sound editor. For others, the term is more associated to the creation of new single sounds. In both cases, the aim of the sound designer is to construct a soundtrack or a number of specific sound effects that make form and function audible. Modern sound design for cinema, games, VR, etc. is either created in performance, through Foley, or is based on the manipulation of sound recordings or digital sound synthesis. Sound design for media production is arguably highly successful and highly sophisticated. A film like Nomadland credited 21 people for sound, and a film like Marvel Studios' Black Widow lists more than 70. Sound professionals working in media production have extensive knowledge of what works and what doesn't in sound design. This is precious knowledge that some researchers, such as myself, are recently attempting to tap into in order to inform sound design disciplines such as sonification. However, this is a tacit, embodied knowledge that is often difficult to observe and formalize. As media productions are cultural forms of expression, they utilize existing cultural references as well as develop new ones that shape the way people listen and interpret everyday sound. Listen to the sound Walter Murch created for these futuristic motorbikes in the first George Lucas film, THX 1138 from 1971. Not too different from today's electric car sounds, don't you think? The history of auditory displays, of which sonification is a type, is much more recent than sound design. While the words auditory displays and sonification start to be used only in the late 20th century, examples of sonification can be found at the start of the century with the Geiger counter. In the industry, concerns about product sound and in particular noise reduction begin in the middle of the century. Additionally, sound starts to be considered as a way to monitor complex displays such as cockpit instruments. With the arrival of computers, issues of accessibility emerge, and the development of music technology such as the MIDI protocol and MIDI keyboards made it easier to connect computer data with sound. The first conference on auditory displays takes place in 1992, and it is followed by a number of books and handbooks that mark the main developments in the field. So what is sonification then? Although more recent definitions have been developed, we take here the original definition from 1999. Sonification is the use of non-speech audio to convey information. More specifically, sonification is the transformation of data relations into perceived relations in an acoustic signal for the purposes of facilitating communication or interpretation. We can see that the definition of sound design by Susini still works well. In sonification, the intentions of the data, the form and function need to be made audible. So we can consider sonification a type of sound design. Sonification and auditory displays more generally have a number of goals ranging, for example, from improving accessibility or data mining. As societies become more and more digitalized, application areas for sonification increase, and you can see a few here. To design sounds that communicate information, it is important to understand how we listen. And there are many modes of listening. Here we use the 3 listening modes as defined by Xiong. Most of the time we use causal listening, which means that we attempt to identify the cause of the sound. If we hear a bark, we assume that there is a dog and we turn to see if we are in danger. Reduced listening refers to listening to the characteristics of a sound rather than its cause. For example, we can listen to a sound paying attention to its pitch in order to judge whether it is higher than another sound. Semantic listening refers to identifying the meaning of a sonic code. We use this when we listen to speech. We recognize the meaning only if we have learned the code. We use it all the time, but only languages that we have learned are easy to listen in this way. So while media sound design relies primarily on causal and semantic listening, sonification tends to rely on the listener actively engaging in reduced listening, something we are not accustomed to. This might be the reason why there are few established standards in sonification, which often requires learning by use and is highly context, case, and audience dependent. Auditory displays can be categorized in Earcons and auditory icons, audification, parameter mapping, and model-based sonification. More recent methods include acoustic sonification and stream-based sonification. All these methods can be interactive or non-interactive. However, the fact that sound is time-based means the sonification is often more effective when the user is tightly embedded within the interactive control loop. Earcons and auditory icons are commonly used to signal events in a user interface. They can also be used to represent multidimensional data points. Earcons are structured musical motifs that are abstract and must be learned to be understood. An example is the Windows 95 opening sound created by Brian Eno. Auditory icons, on the other hand, are metaphorical sounds modeled on everyday sounds. They are analogic and intuitive. For example, the sound of the Mac trash can. It is also possible to create something hybrid such as these auditory icons that represent both a specific drink and the number of alcohol units contained by a typical glass. In Audification, data points are scaled appropriately and played back as audio samples. It works well if the data is time-based and if we aim to hear structures such as noise versus periodicity. Here are two audification examples. The first represents earthquake data, while the second represents gravitational waves from the LIGO. In parameter mapping, data are mapped to sound characteristics such as loudness or pitch. The data becomes a kind of score for the sound. This is the most common sonification method. However, deciding which parameters to use in the mapping is not a trivial issue. We need to consider perceptual issues. For example, changes in pitch are more easily perceived than changes in loudness. Additionally, we need to consider polarity. For example, an increase in weight could be represented with an increase in pitch simply because the values go up. However, a heavy object will produce a lower sound if dropped. So a more ecological mapping would involve inverting the polarity, and so on. Here, an interactive sonification of EMG data from the muscles of a leg. In this case, the roughness of the sound relates to the age of the patient. A younger patient will produce a rougher sound.
So John, if you'd just like to push away, please, just hold you for 3 seconds. Push, and relax. Okay, so 3, 2, 1, and push, and relax.
Model-based sonification is akin to viewing the dataset as a virtual sounding object, which will produce a sonification when excited. Different points of excitation produce different views or sonifications of the dataset. This is better suited for multidimensional datasets. Here we can see an example where a three-dimensional dataset is virtually scanned by a triangular interface. Different paths will create different sonifications. And now Stephen will continue the talk describing acoustic sonification.
Acoustic sonification. Sonifications are usually made on computers with sound synthesis software. Did you know that the first sound synthesizer was actually made out of tuning forks? Could you make a sonification using tuning forks? I wondered. I tried 3D printing variations on the shape of a tuning fork in stainless steel to hear how different they would sound. Some of them didn't really ring that well, but there were some interesting and promising inharmonic partials, vibratos, modulations, and phasing effects. These results were encouraging enough to try experimenting further with, and this time with actual data. I mapped 2 head-related transfer functions, each consisting of 100,000 points, onto the shape of a pair of bells, left and right bells, and you could clearly hear that the data sets were different by playing these two bells. So here we are in real time generating sounds from 10,000 data points and hearing the difference between, from 100,000 data points, and hearing the difference between these two data sets without the use of computers or electronic circuits, just using acoustics. Next, I started playing around with singing bowls. The chemo singing bowl, which I've shown here, is made from the blood pressure measurements during a year of chemotherapy. As you can see, the chemotherapy has a big effect on the human body, and the blood pressure is extremely irregular. The chemo singing bowl was designed as a gift for my friend who provided this data set, and I hoped it would cheer her up and make a beautiful and uplifting sound. However, when it was played, it clanked like a tin can. Apparently, the irregularity of chemotherapy blood pressure does not make a very pleasant sound. It's very inharmonic. It sounds just like I felt, she said. I realised sonifications don't have to sound beautiful to sound right. Trained ears and correlation coefficients. In a social science study of the International Community for Auditory Display, Alexandra Supper identified a tension between two approaches to research. One group she called the correlation coefficients had training in psychology, cognitive science, and human-computer interaction, and their aim was to build a general theory of sonification using controlled laboratory studies. The other group she termed the trained ears had more musical and sound design backgrounds, and they were more interested in the way the sounds provided functionality and the effect of the sounds in practice. Research through design. Bill Gaver, who established the auditory icon technique that Sandra introduced earlier, observed that the influx of graphic and product designers into the field of human-computer interaction had caused a clash of cultures with the established cognitive scientists in that discipline. He proposed that the HCI conferences should accept design research as a legitimate form of knowledge. Art plus science equals design. Nigel Cross proposed that design is a third way of knowing that is distinct from art and science. Design focuses on the knowledge of the artificial man-made world, using modelling and synthesis to imagine and realise practical outcomes. Data sonification is clearly a part of this artificial realm. Interaction design. Interaction design has defined itself as an explicitly designed discipline, distinct from the field of human-computer interaction. This has allowed a holistic focus on qualities of human experience that include physical, sensual, cognitive, emotional, and aesthetic issues, which are far outside the controlled laboratory paradigm, as well as extending to more fuzzy concepts such as fun and playfulness. Human-centered design. Audio's human-centered design process has iterative phases of inspiration, ideation, and implementation. These phases encouraging alternating modes of divergent and convergent thinking. Sonic information design. Sonic information design aims to bridge the tension between art and science in the field of sonification. Like interaction design, it focuses on the qualities of human experience that include emotional and aesthetic issues, as well as fun and play. It draws on the divergent convergent design process with the phases of inspiration, ideation, and implementation. Evaluation is a key component and can draw on both qualitative and quantitative methods as necessary and without prejudice. Examples of sonification are key forms of documentation that speak just as loud or perhaps more loudly than textual descriptions or statistics. TADA framework. TADA stands for Task-Oriented Data-Sensitive Framework. This task-oriented is inspired by the idea that sonification, like language, is a tool. As the philosopher of language Wittgenstein said, ask not the meaning, but the use. Data sensitive. Data is not homogeneous. It is important to understand that the type, structure, and organization of the data should be reflected in the design of the sonification. Blood pressure data should sound different from stock market data. Perceptual alignment. Perception is an active information-seeking system, according to J.J. Gibson, who is the father of perceptual psychology. Information needs to be aligned with the perceptual system to be understood correctly. Display device capabilities. The designer needs to consider the technical capabilities of the sound production software and hardware and take advantage of these to optimize the sonification display. Stream-based sonification. The theory of auditory scene analysis provides a basis for the perceptual alignment of sonic information using principles of Gestalt grouping and segregation. Sifting gold from dirt is an example of stream-based sonification that uses sequential grouping to segregate gold from dirt in a dataset containing 300 samples of six-dimensional soil samples. The six-dimensional samples are mapped with 6 parameters of an FM synthesis algorithm that produces widely varying and categorically different timbres. The FM algorithm has been tuned so that gold samples fall in a higher, brighter timbral region. The sequential playback of 20 samples per second causes the gold to perceptually group and segregate from the dirt. The ship turbine example is a real-time monitoring system where 7 sensors provide data about the operation of the ship's engine. In this scenario, the sensors gradually go into a danger zone as the turbine breaks down. This stream-based sonification employs the fundamental basis of perceptual streaming known as the Van Norden gallop. By alternating the value of each sensor with a repeating galloping complex, sensors go into danger zone. They group with the gallop complex to produce various different rhythms until all the systems go critical, creating an urgent alarm. Note that there is no symbolic mapping, and the system state generates the perceptual groupings. The virtual Geiger counter uses the metaphor of a Geiger counter to represent 12 different variables that have been measured down an oil well log. Each independent variable has a different timbre, so there are 12 distinctly different sounding Geiger counters. The brightness and rate of each Geiger counter varies with the data value. Variables with similar values will perceptually group, allowing the user to hear correlations as a single stream and decorrelations as separate streams.
Indicates that there's a very high nutrient porosity while the bulk density is very low. So that means, or might indicate gas below is a zone where the nutrient porosity decreases while the bulk density increases. So that's why this region is gray. And this might indicate oil or water. It's not really clear what it is.
That's this region here. And in this region where the stripes are, you can also see a quick change in the gamma radiation on this lens and also hear it on the Geiger counter. The third well log
indicates that there's a very high nutrient.
In summary, sound design is the intentional design of sounds for a specific purpose. Although there is a canon of established techniques for sonification, the lack of theory or standard principles has led to a tension between scientific and artistic approaches. This tension can be resolved with a design-oriented approach to sonification that's based on intention. Sonic information design provides a process for the intentional mapping of data into sound for a specific purpose. The human-centered design process has cyclic phases of inspiration, ideation, and implementation. Design research draws on multiple epistemological approaches as necessary. Various methods of evaluation are vital in this cyclic process. Well, here we are at the end. Thanks for listening, and feel free to contact me, Stephen Barris, or Sandra Pauletto, if you'd like to talk about some of these things further. And here at the end of the slideshow, there are some references if you want to delve into some of the topics further as well. Okay, bye.